Any questions? Okay, let's look at those. Six B. All right, so let's take a look at those. So for number 4, we're starting off with, we've got the differential equation. So we've got d squared r dt squared is equal to negative 32k. Okay. And we are given initial conditions of r of 0 is equal to 100k and dr dt evaluated at t equals 0 equals 8 in the I direction plus 8 in the j direction. Okay, so if I take a look at this, okay, so dealing with this differential equation, so we've got that d squared r d t squared is equal to negative 32k direction. So if we integrate this, it's going to become dr dt, and this is going to be equal to negative 32 tk plus c. Okay, so what we're going to do first is to use this initial condition. Okay, so we know that in place of dr dt, we're going to put 8 in the I direction plus 8 in the j direction. And that's equal to, if we plug in t, 0 for t here, this term is going to go away, so we just have c. So you should find that dr dt is going to be equal to, it won't be negative 8, but it will be 8 in the I direction plus 8 in the j direction minus 32t in the k direction. Okay? Any questions there? Okay, so next, what we're going to have is we're going to integrate again. Okay? So when we integrate, the left side becomes r, and this is going to be equal to, this is going to be 8t plus c in the I direction plus 8t plus c in the j direction, then minus 16t squared plus c in the k direction. And then now what we're going to do is to use the other initial condition. Right? So we're going to have, in place of r of t, we're going to put in 100k. And that's going to be equal to, all right, basically, when we plug in 0 for t for all these pieces, we're going to have that first part is going to be c in the I direction plus c in the j direction, then minus, wrong way, excuse me, then minus c in the k direction. Now, since there's no I in j, that means that terms goes away. So that means that c, negative c, is equal to 100, or c is negative 100. But keep in mind, it's only with the k component. These other two c's, since there's no I and j components on the other side, those c's are 0. Okay, so you'll get that r of t is going to be defined as 8t in the I direction plus 8t in the j direction minus 16t squared minus 100 in the j direction. That's what I put. And put plus 100. Yeah, it will be plus 100 if, and this is the k direction. So the answer that I have is correct because all I got to do is run the negative through the parentheses. Okay. Any questions there? Okay. All right, so next, looking at 6b, okay, so in this portion says for the same initial speed, find the two firing angles that make the range equal to 6m, okay? So we know that the range is equal to the initial velocity squared over g times the sine of 2 alpha. Okay. All right. So in this one, in place of the range, we're going to put 6. Now we are working in meters, so the velocity is going to be 9.8. We're going to square that. G. Oh, did I tell us the initial velocity? Oh no. We've got the initial velocity from part A. Okay, so the initial velocity from part A was what? So 9.9. So we're gonna put 9.9 here squared. And then we're gonna have 9.8 for the gravity times the sine of 2 alpha. Okay. So basically what we're going to do is to solve for this. Now 6 times 9.8 divided by 9.9 squared. So I'm going to get 0.59938. That's going to be equal to the sine of 2 alpha. So if I take the sine inverse of that, I'm going to get that 2 alpha is going to be equal to 36 point, I think, let's see, did I do 1 decimal place? Yeah, 1 decimal place. So I'm going to 36 point, basically 9. Now, you've got to remember that sine is going to be positive in another quadrant. It's going to be in quadrant 2. So your other answer is going to come from quadrant 2. So if I do 180 minus 36.9, that's going to give me 143.1. But keep in mind that is 2 alpha. So if I want alpha, I'm going to divide each by 2. So 36.9 divided by 2, that's going to give me basically 18.5. And then the other one, 143.1 divided by 2, it's going to give me roughly about 71.6. And I think that's what roughly what I put the answers down to. Okay. Any questions there? All right, and then the last one we have is for problem number 7. It says what 2 angles of elevation will enable for a projectile to reach a target 60 kilometers downrange on the same level as the gun if the projectile's initial speed is 400 meters per second. So with this particular thing, what we're dealing with here pretty much is going to be similar to what we did for 19. Okay, I mean for 6B. So we're going to have we're going to use the range is equal to initial velocity squared over g times the sine of 2 alpha. Now, they tell us what the range is. It's going to be 16 kilometers, but keep in mind that the speed is in terms of meters, so we need to convert that over to meters. So we're going to have 16,000 meters, and that's going to be equal to initial velocity was 400. We're going to square that divided by gravity, which is 9.8. We got the sine of 2 alpha. Okay, so if we look at this, all right, so when we do this calculation, we're going to end up with 0.98 is equal to the sine of 2 alpha. So if we take the sine inverse of both sides, so we're going to get that 2 alpha. So one of the angles we're going to get is going to be 78.5. Now, we do know that sine also is positive in quadrant 2. So if we do 180 minus that angle, we're going to get 101.5. So if we divide each by 2, so this will give us about 39.3 degrees. And the second one is going to be about 50.8 degrees. Oops. Those are the answers I gave. Yeah. Okay. All right. Any other questions? Okay, so let's continue on where we left off on Tuesday. So we were getting ready to work on the last problem from of the section dealing with curvature of a curve. Okay, and in the last example, we were looking at this. So r of t is equal to hyperbolic cosine of t in the I direction minus hyperbolic sine of t in the j direction plus t in the k direction. And in this, we are asked to find the unit tangent, unit normal, the binormal, and the curvature. Okay, so let's start off with the unit tangent. So we need the velocity vector first. So if we find the velocity vector, we're going to end up with hyperbolic sine of t in the I direction minus hyperbolic cosine of t in the j direction plus 1 in the k direction. Okay. All right, so next we need the magnitude of this. So if we do the magnitude, we're going to have the square root of hyperbolic sine squared of t plus hyperbolic cosine squared of t plus 1. Any questions there? All right, so at this time, we have to we're going to use identities in order to be able to simplify this. So if I take a look at this, what I know is that hyperbolic sine squared of t plus 1, that's going to be equal to hyperbolic cosine squared of t. So essentially what I'm going to have is the square root of 2 times the cosine hyperbolic squared of t, or end up with the square root of 2 times the cosine hyperbolic of t, hyperbolic cosine of t. Okay. Any questions there? Okay, so now what we're going to do is to go through and find the unit tangent. So the unit tangent t is going to be 1 over the magnitude of velocity times the velocity. Okay, so it's going to be 1 over the square root of 2 times the cosine hyperbolic of t. And then we're going to multiply that by, and we found v to be sine hyperbolic of t in the I direction minus cosine hyperbolic of t in the j direction plus 1 in the k direction. Okay, now we do want to multiply this out so it makes our derivative a little bit easier when we are dealing with the unit normal. So we should end up with 1 over the square root of 2 times tangent hyperbolic of t in the I direction minus, we're going to have 1 over the square root of 2 in the j direction, because the cosine hyperbolics are going to cancel. And then we're going to end up with plus 1 over the square root of 2 times secant hyperbolic of t in the k direction. Any questions? All right. Is everyone okay what we've done so far? Okay. All right. So next, we're going to find the unit normal. Okay. So for the unit normal, we need to take the derivative of the unit tangent in respect to t over the magnitude of the derivative of the unit tangent in respect to t. Okay. So we set the unit tangent, which was defined as 1 over the square root of 2 tangent hyperbolic t in the I direction minus 1 over the square root of 2 in the j direction plus 1 over the square root of 2 secant hyperbolic of t in the k direction. Okay. So if we take the derivative of this function, right? So if we take the derivative of the first piece, what will we get?
One over root 2 secant square t.
So hyperbolic secant squared of t in the I direction. All right. Now, what would be the derivative of the second component?
0.
Okay, so we're just going to ignore that. And then if we take the derivative of the third component, what are we going to get?
Negative 1 over root 2 secant t tangent t.
And that's in the k direction. Okay. Any questions there? Okay, so next we're going to look at the magnitude of this. Okay, so that's going to be the square root of the first term. If we square that, it's going to end up being 1/2 secant hyperbolic to the fourth of t plus, and then for this next term, it's going to be 1/2. We're going to end up with secant hyperbolic squared of t tangent hyperbolic squared of t. Okay. So now, what do you think I could do?
Factor out 1/2 secant hyperbolic square t.
Okay, so let's do that. So, oops, I don't want that slide in there. What happens when I don't complete them the slides. Okay, so this is going to be the square root of 1/2 secant hyperbolic squared And then what I'm going to have left is secant hyperbolic squared t plus tangent hyperbolic squared of t. Okay. Now, if we take a look at our identities, we know what this is going to be equal to. So what is that expression equal to? Yes, it's equal to 1. So really, all we have is the square root of 1/2 times the secant hyperbolic squared of t, which essentially is going to be 1 over the square root of 2 times the secant hyperbolic of t. Okay? Any questions there? All right, so let me go back a couple of slides. So fill in, okay? So for this, I'm going to have 1 over the square root of 2 times secant hyperbolic of t times. In place of this, I'm going to put in this expression here. So I've got 1 over the square root of 2 times secant hyperbolic squared of t in the like direction, then minus 1 over the square root of 2 times secant hyperbolic of t tangent hyperbolic of t in the k direction. Okay. And I'm just going to switch colors to do the simplified answer. So when we multiply this out, okay, so when I take this times this, what will I have left over?
Secant hyperbolic t.
Right. In the ith direction. And then when I take this expression times this, what do I have left?
Negative tangent hyperbolic t in the k direction.
Correct. I'm just going to put parentheses around that. So that is our unit normal. Any questions there?
Wait, can you hear me?
Yes, I can.
Oh, so why did it become a negative when we did the derivative? When it was
Remember the derivative of both for the last 3 hyperbolic trig functions. So for cotangent, for secant, and for cosecant, they're all negative.
Oh, okay, yeah, never mind. I was looking at the wrong derivative.
So do remember that the last 3 trig functions on the hyperbolics don't follow our traditional derivative rules for trig. They are going to be those. All 3 of those are negative. Okay. Any other questions? Okay, so we found that the unit tangent was defined as 1 over the square root of 2, and I remember correctly. Okay. 1 over square root of 2 tangent hyperbolic of t in the ith direction plus 1 over square root of 2 in the j direction. I think minus 1 over square root of 2. Let me make sure before I do that. No, excuse me, plus, sorry. Plus 1 over square root of 2 secant hyperbolic of t in the k direction. We found that the unit normal was just going to end up being it started off as tangent hyperbolic, correct? For the unit normal, did it start off tangent hyperbolic? Or was it secant hyperbolic?
I think it's secant hyperbolic in the I direction.
Okay, so secant hyperbolic of t in the I direction, and then we ended up with
Negative.
minus tangent hyperbolic of t in the k direction. Okay, so those are two. So next, we want to find the binormal. So we've got our ijk components. So for here, we're going to have 1 over square root of 2 tangent hyperbolic t, 1 over square root of 2, and then 1 over square root of 2 secant hyperbolic of t. And then for the last row, we have secant hyperbolic of t, 0, and then negative tangent hyperbolic of t. Okay, so if we look at the I component of this, we're going to end up with negative 1 over the square root of 2 tangent hyperbolic of t in the I direction. For the j component, we're going to end up with minus, we're going to end up with negative 1 over the square root of 2 tangent hyperbolic squared of t minus 1 over the square root of 2 secant hyperbolic squared of t, and that's going to be in the j direction. And then plus, then for the k component, we're going to end up with just negative 1 over the square root of 2 secant hyperbolic of t in the k direction. All right. Any questions on how I got each of those pieces? Now, we can clean this up a little bit. The first component stays as it is. There's nothing you can do about that. Okay. Now, for this middle component, for this, what is it actually equal to? Yeah, so the middle term is just going to clean up nicely to just positive 1 over the square root of 2 in the j direction. And then for the last component, you can't do anything about that, so we're just going to leave it as it is. So I can bring out a negative, and then I have 1 over the square root of 2 secant hyperbolic of t in the k direction. Now, one thing you can do, which I didn't do, this negative here, you don't have to have attached. You can pull it out front, but it doesn't matter which it is. Now, just keep in mind that the reason why this middle term, and not blow it up so you can see, the reason why this middle term is just this, keep in mind that you can factor out a negative 1 over the square root of 2, and by the hyperbolic identities, tangent hyperbolic square t plus secant hyperbolic square t is 1. So I have 1 times 1 over the square root of 2. That's why we just end up with the square root of 2, 1 over the square root of 2 for the middle term. Okay. Any questions? All right, so the last thing we need to do is the curvature. So for the curvature, kappa, that's going to be 1 over the magnitude of the velocity times it by the magnitude of the derivative of the unit tangent. Now, we said that the magnitude of the velocity was equal to what?
Root 2 cos hyperbolic square t. But yeah, square root.
Okay, and then we said that the magnitude of the derivative of the unit tangent was what?
One over root 2 secant hyperbolic t.
Okay, all right, so what essentially is this going to be equal to? When you multiply this out. Yeah, so we can do it as 1 over 2 hyperbolic cosine square t, or we can say it's going to be 1/2 secant hyperbolic square root of t. It's the same answer. Okay, so you can write it either way. Okay. Any questions? Okay. All right, so that is it for section dealing with curvature in space. So next, let's move to our next section dealing with the tangential and normal components of acceleration. All right, so in this section, we do one of the first things we do, you are given a definition for the binormal, and we've already been practicing doing the binomial and everything. But actually, the formal definition of the binomial, it's a unit vector orthogonal to both the unit tangent and the unit normal. You always got to remember that when you're doing a cross product of two vectors, you're going to create a vector that is basically orthogonal to the two vectors. Okay. The next one is taking a look at how to rewrite the acceleration vector in terms of the unit tangent and the unit normal. Okay, so acceleration can be written as a value a sub t times the unit tangent plus a sub n times the unit normal. Okay, so basically you can essentially what you can do, you can write the unit vector sort of as a linear a linear combination of the unit tangent and unit normal. Okay, now how we calculate each of these for a sub t. Now when we're doing this, we're never really ever worried about doing the calculations of actually finding the unit tangent or the unit normal. What we're looking for is what a sub t is and what a sub n is. Okay, so to find a sub t, all right, basically what you're going to do is you're going to take the derivative in respect to t of the magnitude of the velocity. Okay, and to find a sub n, the shorthand way of finding a sub n, it's going to be the square root of the magnitude of the acceleration vector squared minus a sub t squared. Okay. And then the last thing we have that we will be working in this section is dealing with torsion. Okay, and basically torsion is, it's going to be a function that is going to a function of a smooth curve. Torsion function is a function of a smooth curve is defined as basically we're going to take the negative of the derivative of the binormal in respect to s and then dot it with the normal vector. Okay, now in your notes I give you kind of a long complicated formula. Let me give you a different formula for torsion. Okay, so torsion, you can say that it's tau. This is the Greek letter tau, T-A-U. Okay, and it's going to be equal to the cross product of the first and second derivative of r. We're going to dot it with the third derivative of r. And then we're going to divide it by the magnitude of the cross product of the first and second derivative squared. All right, so let's take a look at this as some examples of doing this. All right, so our first example, it's asking us to write the acceleration vector in the form of a sub t times the unit tangent plus a sub n times the unit normal without finding the unit tangent or the unit normal. So for the first one, it tells us that r of t is equal to 1 plus 3t in the I direction plus t minus 2 in the j direction minus 3t in the k direction. Okay, so in order to do this, all right, so again, we're looking at taking this and write it in this form here. And again, we're not trying to find what the unit tangent or the unit normal vectors are. So first, let's find a sub t. Okay, So a sub t is going to be the derivative in respect to t of the magnitude of the velocity vector. So what we're going to do first is to find the velocity vector. Well, that's going to be 3 in the I direction plus 1 in the j direction minus 3 in the k direction. So now what we want to do is to find the magnitude of this. So that's going to be the square root of 9 plus 1 plus 9, or the square root of 19. Okay. Any questions there? So what I'm going to do for a sub t, I'm going to take the derivative in respect to time of the magnitude, which is the square root of 19, of the velocity, which is going to give us what? No, because the I component is just 1 plus 3t. Derivative of that is just going to be 3. So 3 squared is 9, yes, for that in the velocity. Yeah, no, it's a 9, sorry. Okay, so what would be the derivative in respect to t of the square root of 19? Be 0. Okay, so that is going to be what a sub t is. So next, we need to calculate a sub n. A sub n is going to be the square root of the acceleration squared minus a sub t squared. Okay. Well, if I look down here, okay, if I find the acceleration vector, well, acceleration vector is going to be 0 in the I direction, plus 0 in the j direction, plus 0 in the k direction. So the magnitude of that is going to be what? So what would be the magnitude? Yeah, magnitude of the acceleration vector is 0 minus, we already found that a sub t was 0, so we end up with 0. So for this problem, in place of a sub t, we put 0. In place of a sub n, we put 0. And this will be our acceleration vector written in terms of the unit tangent and the unit normal. Any questions? Okay, so for the second problem, we have this. We have that r of t is defined as t times the cosine of t in the I direction, plus t times the sine of t in the j direction, plus t squared in the k direction, and they tell us that t is equal to 0. Okay, so we're going to use that to help us out to actually come up with values instead of leaving things in a function notation. Okay, so again, what we want to do is take the acceleration vector and write it in terms of component forms of the unit normal unit tangent and the unit normal. Okay. So the first thing we're going to do is to find a sub t, which again is the derivative with respect to t of the magnitude of the velocity. Okay. So first, let's find the velocity vector. So v of t. All right. So if we find that, we're going to end up with negative t sine of t plus the cosine of t in the right direction plus t cosine of t plus the sine of t in the j direction plus 2t in the k direction. Any questions there? Okay, so next, what I'm going to do is to find the magnitude of the velocity. Well, that's going to end up being the square root of, okay, it's going to be negative t sine of t plus cosine of t squared plus t times the cosine of t plus the sine of t squared plus 2t squared. Now, with this problem, as much as we would love there will be a shortcut, there's really not. Okay, so we've got to do due diligence and square this stuff out. Okay, so what we're going to have is this. We're going to have square root of, okay, so the first term squared out, we're going to end up with t squared sine squared t minus 2t sine t cosine of t plus cosine squared t plus. Second term squared out is going to be t squared cosine squared t, and it's going to be plus 2t sine t cosine of t, and we're going to have plus sine squared t plus, and the last term squared is 4t squared. And keep in mind that this is still under the radical. Now, what's going to happen is that some things are going to cancel and some things are going to be able to be combined. So I'm looking at this, I'll be able to cancel the negative 2 sine t cosine t with the positive 2 sine t cosine t. So that term is gone, which is good. Okay. Then next, I've got the t squared sine squared and t squared cosine squared. Well, that's just going to give me what? So t squared sine squared t plus t squared cosine squared t. Yes, that's just going to give me t squared, which I'm happy about because I'm getting rid of trig. All right. Next, I've got sine squared, cosine squared here, sine squared here, which is just going to give me what? 1. And then don't forget the 4t squared. So really, this just cleans up to nicely 5t squared plus 1. questions? Okay, so let me back up a slide. So in place of the magnitude of v, I'm going to have dt, derivative with respect to t of the square root of 5t squared plus 1. Well, that's going to end up being 1/2 times 5t squared plus 1 to the negative 1/2 times 10t. Oops, left off the t. Okay. Everyone okay with that? All right, so if I evaluate now I'm going to use my time. So if I evaluate this derivative at t equals 0, what will I get?
0.
I get 0. So in place of a sub t, I'm going to put 0. Now, it's not always going to be 0. It just happened to be this way in the two examples I'm doing. Okay? Any questions there? Okay, so what we have to do next is we need to deal with a sub n. Now, keep in mind that a sub n does require us to do the magnitude of the acceleration vector, and then we're going to subtract off a sub t of 0. Okay, so let's deal with that. All right, so first let's find the acceleration vector. So we're going to take the derivative of the velocity. So if we take the derivative of the velocity, we're going to end up with this. We're going to have negative t cosine of t minus sine of t minus sine of t in the I direction, plus negative t sine of t plus cosine of t plus cosine of t in the j direction plus 2 in the k direction. Okay. So when we do the derivative of that, this is what of the velocity, this is what we're going to end up with. It's going to generate our acceleration. Now, I can clean this up a little bit. So it's going to be negative t cosine of t minus 2 sine of t in the I direction plus negative t sine of t plus 2 cosine of t in the j direction plus 2 in the k direction. Okay, so now let's look at the magnitude. So we're going to have the square root of negative t cosine of t minus 2 sine of t squared plus negative t sine of t plus 2 cosine of t squared. And then we're going to have 2 squared, which is, I'm just going to put 4 there. And again, there's no short way of doing this. You just have to multiply it out. Okay, so we're going to end up with the square root of, all right, we're going to have t squared cosine squared t plus 4t cosine of t sine of t plus 4 sine squared t plus t squared sine squared t minus 4 t cosine of t sine of t plus 4 cosine squared t, then plus 4. And again, keep that in mind, that's under the radical. Now, one thing I do want you to keep in mind is that these problems are designed so that they come out nice. Okay, so that things will cancel, so you don't have such ugly things going on. So it may look ugly while you're working it, but it cleans up once you start simplifying and get everything multiplied out. So when I look at this, these terms are going to cancel. These terms combine to give you just t squared. These terms combine to give you just 4, and then you got another 4. So you've got the square root of t squared plus 8. Let's see here. Oops. Is this slide you're referring to? Okay. All right. Okay, so let's find, so what we're going to do is we're going to find this when t is 0. So when we do that, we're going to have the square root of 0 plus 8, square root of 8, which is 2 times the square root of 2. So a sub n is going to be the square root of acceleration vector squared minus a sub t squared. All right, so we take the square root of, if we square the acceleration vector, we're just going to get 8. The magnitude of the acceleration vector, we're going to get 8. Minus, we found that a sub t was 0. So we have the square root of 8, which is going to be 2 times the square root of 2. So there's our a sub n. Any questions? So let me just go back to here. So in place of this, we're going to put in 2 times the square root of 2 times the unit normal vector. Any questions? Okay, so at this time, let's take a 10-minute break, give your brain a chance to relax and digest this. And then we'll come back and we'll probably only, I think I've got 2 more examples in this section. We'll get done probably just one of the 2 examples, okay? Because they do take kind of a long time to do them, all right? So let's do our 10-minute break and then we'll come back. Okay, so let's look at our next example. All right, so our next example, we're asked to find the unit tangent, unit normal, binormal, kappa, and tau. Okay, so in this problem, we've got a lot of stuff that we got to do. All right, so starting off, the problem reads that we've got that r of t is defined as e to the t sine of 2t in the I direction plus e to the t cosine of 2t in the j direction plus 2e to the t in the k direction, and it tells us that t is equal to 0. Okay, so what we're going to do is we're going to actually find all these vectors and come up with the numerical values. But one of the things I have to caution you about is that you still have to do all the work to create the vectors initially in variable form, because otherwise, in prime example, when you do the unit normal, if you're taking the derivative of the unit tangent in its evaluated form, you're going to get 0, okay, because it's going to be all constants. So just because you come up with the constant answers doesn't mean, unless it comes out that way when you're doing in a variable form. Otherwise, you always have to make sure you go back to the variable side, because otherwise you're going to get 0 for your answer, which is not what you want. Okay, so starting off with the unit tangent. Okay, so first of all, we need the velocity vector. So for the velocity vector, we're going to have this. We're going to have 2e to the t cosine of 2t plus e to the t sine of 2t in the I direction, plus, next one is going to be negative 2 e to the t sine of 2t plus e to the t times the cosine of 2t in the j direction plus 2e to the t in the k direction. All right, so next we need to find the magnitude. Okay, so we're going to have the square root of, right? I'm going to do kind of a sneaky little trick with these to make it work a little bit better. It'll work somewhat better. What I'm going to do is, for this, I'm just going to write it out first. Okay, so this is what we're going to have. So essentially what I'm going to do with this to make our life easier is that basically every term has an e to the t, okay? And it's going to end up being a e to the t squared that is going to come out, all right? So what I'm going to do is I'm going to go ahead and just factor that out. So I'm going to have the square root of e to the 2t. That's going to come out. So what that does is it takes out these e to the t, these extra e to the t's. It takes these out. Okay, so when I factor this out of the parentheses, I am going to square it, so it's going to become e to the 2t. Same way here, I'm going to factor out the e to the t, but I do have to square it, so it becomes e to the 2t. So this comes out of all of this. So now what I've got left, in the first one, I've got 2 cosine 2t plus sine 2t. And I'm going to square that. All right. So when I do that, that's going to give me 4 cosine squared 2t plus 4 cosine 2t sine 2t plus sine squared 2t. Okay. And unfortunately, I'm kind of out of room. All right, so what I'm going to do, I'm going to write this last line on the next page. Okay. All right, so that's this first piece squared. Now I'm going to do the second piece squared, so it's going to end up being plus 4, it's going to be sine squared 2t. The middle term is going to be a negative 4 cosine 2t sine 2t. And I'm going to have plus cosine squared 2t. And then at the very end, I'm going to have a plus, I think it's plus 4. Let me make sure. Yes, be plus 4. Okay, so that's factoring out the e to the 2t from the terms initially and then just squaring this out. So this is what it looks like. So what happens here is that this term and this term cancel, which is nice. I can combine this term and this term. And I end up with just 4. Then I can combine this term and this term, which will give me 1. And then I can't forget this term. So I end up with the square root of 9e to the 2t. So when I take the square root of this, I just end up with what? Yeah, I just end up with 3e to the t. Okay, as I said, these problems are designed so they come out nice and clean. So for the unit tangent, it's going to be 1 over 3e to the t times, then I'm going to multiply that by the velocity, and the velocity is defined as follows. So we have 2e to the t, cosine of 2t plus e to the t sine 2t in the I direction, plus, then I've got negative 2e to the t sine 2t plus e to the t cosine of 2t plus 2e to the t, excuse me, I forgot the j direction, and this is times k direction. Any questions there? Okay, so if I clean this up, all right, we're going to have that t equals 2/3 cosine of 2t plus 1/3 sine of 2t, and this is in the I direction, plus, and then I'm going to have a negative 2/3 sine 2t plus 1/3 cosine 2t in the j direction plus 2/3 in the k direction. So this is what the unit tangent vector cleans up to be, which is nice. So now what I'm going to do is to find what it would be evaluated when t is equal to 0. Okay, so if I plug in 0, I'm going to end up with 2/3 in the I direction plus 1/3 in the j direction plus 2/3 in the k direction. So this will be what the unit tangent vector would be evaluated at t equals 0. Any questions? Okay, so next, let's find the unit normal. Okay, so the unit normal, we need the derivative of unit tangent in respect to time. So if we take the derivative of the unit tangent in respect to time, we're going to end up with negative negative 4/3 sine 2t plus 2/3 cosine 2t, as in the I direction, plus negative 4/3 cosine of 2t plus, actually it's going to end up being minus 1/3, it's not 1/3, sorry, it's going to be 2/3. Two-thirds sine of 2t in the j direction, and then for the k component, it's going to be 0. Okay, so this is what we're going to get for the derivative of the unit tangent in respect to time. Any questions? Okay, so the next piece is that we need the magnitude. So if we find the magnitude, all right, so what we're going to do is to take the negative 4/3 sine 2t plus 2/3 cosine 2t. We're going to square that, okay, and then add that to negative 4/3 cosine 2t minus 2/3 sine 2t and we're going to square that, okay, and there was no, and if we look at this, there was no k component, so we don't have to worry about that. So it's just these two pieces here. So if I square this out, I'm going to have 16/9 sine squared 2t minus, we're going to have 16/9 sine 2t cosine 2t plus 4/9 cosine squared 2t plus, we're going to have 16/9 sine squared 2t. We're going to end up with plus 16/9 sine 2t cosine 2t plus 4/9 sine squared 2t. Now, once we get here, we realize that things, it does
Sorry,
simplify nicely. Mm-hmm.
I'm sorry, I think it is cos squared 2t in the like 16/9, the fourth one. I mean,
Oh, I put sine, sorry. Okay, thank you. All right, so these will cancel. These we can combine, and they're going to give us just 16/9. These we can combine, and they're going to give us just 4/9. So we basically have the square root of 20/9, which is 2 square root of 5/3. Okay? So that's what dt, the magnitude of dt dt is. Okay. Any questions? Okay, so let's go back a slide and find what the unit vector, unit normal is going to be. Okay, so it's going to be 1 over this. So all it's going to do is just flip this fraction. Okay, so this is going to be 3 over 2 times the square root of 5 times our derivative component. So that's going to be the -4/3 sine 2t plus 2/3 cosine 2t in the I direction plus -4/3 cosine 2t minus sine, excuse me, left out just a little bit, minus 2/3 sine 2t in the j direction. Okay. All right. Now, if we evaluate it, let me write it down real quick. If we evaluate it, we're going to end up with so if we look at the unit normal evaluated at t equals 0, we're going to end up with a result of 1 over the square root of 5 in the I direction minus 2 over the square root of 5 in the j direction. So it cleans up that nice. Any questions? You want this slide or this slide? Any questions? Okay. All right. So the next two pieces of this we can do really fast because we don't typically use the binomial to create something else. So what we can do is just go ahead and deal with the binomial and use the evaluated forms of the unit tangent and unit normal. Okay. And the same thing with the curvature. We can with that, we can go ahead and use the evaluated forms of the things. Okay, so let's look at those real quick. So for the binormal, we're going to have our I, J, K component. Okay, now for the unit tangent, when we evaluated it, it was 2/3, 1/3, 2/3. 2/3, 1/3, 2/3. For the unit normal, which is right here on this page, which is nice, it's 1 over the square root of 5, negative 2 over the square root of 5, and 0. Okay. Now, keep in mind that essentially what we're doing here by doing this way, we're going ahead and finding the binomial when t is equal to 0. Okay. So we're not actually looking for a vector function per se for the binomial. We just want to find what that binomial vector actually is. Okay. So if I look at the ith component, I'm going to end up with 4 over 3 square root of 5 in the ith direction. For the j component, I'm going to end up with plus 2 over 3 square root of 5 in the j direction. And then for the k component, I'm going to end up with, so I'm going to end up with minus 5 over 3 times the square root of 5 in the k component. So this would be our binomial vector when t is 0. Any questions? Okay, so the last thing I'm going to find of this problem is kappa, which is the curvature. So it's going to be 1 over the magnitude of the velocity times the magnitude of the derivative of the unit tangent. Okay, so the magnitude of the unit derivative of the unit tangent we found happens to be 2 to the square root of 5 over 3. Okay, for the velocity, the magnitude of the velocity, let's see here, where do we find that? Okay, so this is the velocity, but if we evaluate this at 0, we're going to get a value of what? So if we evaluate this at 0, we're going to get a value of 3. So that's what we're going to use. This is a 3. So we're going to have 1/3 here. So we're going to end up with 2 square root of 5 over 9. And that would be our curvature. Again, this is when the curvature when t is equal to 0. Any questions? Okay, so we're going to stop here because I don't have enough time to go through the torsion. So I will pick up on that on Tuesday of next week. Okay, so at this time, you should be working on the homework over curvature in space. Let's see, early section. Okay. I think I've already signed the homework for arc length, so that was assigned the previous class. So just really the only thing right now is curvature in space. Okay. Quiz 4 is available, and it's due Tuesday. Okay. So quiz 4 is available, and it's due Tuesday. Any questions? All right. Well, that is it for today. You guys have a great rest of the day. Happy Valentine's. Happy President's Day. And I'll see you guys on Tuesday.